Hello, my name is Professor Shannon Betcher. Today I'm going to talk about porous electrode theory. This information is from Fuller and Harb's book, Electrochemical Engineering, Chapter 5. You should own this book if you're taking this course. Well, why do we care about porous electrode? Well, here's an electrode that consists of an array of cylindrical pores inside a solid. So the solid is sort of rendered here, and the pores go in and they have a cylindrical geometry with some radius r. And this idealized geometry can be used to describe or think about how many types of electrodes work. Practically, they're important in batteries and fuel cells and pretty much any electrochemical device where you want to pass a lot of current per unit time to drive a reaction. Let's take as an example the lead acid battery. In the lead acid battery, you start in the charged state after electrochemically charging the battery with lead oxide on a lead grid. So here's a lead alloy grid with a lead oxide paste on it. And that's our positive electrode. At our negative electrode, we have a lead metal grid. As this electrode discharges, the electrons flow from the negative electrode to the positive electrode and do work along the way. And that's how you extract chemical energy from the battery. And as you do that, you convert this lead oxide coating to a lead sulfate coating. And both these have substantial nano and microstructure, as illustrated here in this picture, supported on this high surface area grid. So the electrochemistry in a battery is inherently multi-scale. It includes the macroscopic components, the grids, and the current collectors. It includes the micro components, the microscale components, which are the metal oxide and metal deposits that are actually electrochemically active. And it further includes structure at the nano and atomic scale that describe how this battery works. And we need to understand how the flow of reactants, for example, sulfate, water, and the movement of charge and electrolyte species occur in such a battery. Another example is a fuel cell. A fuel cell has, again, an anode, cathode. At the anode, you oxidize H2 to make protons. The protons go across a proton-conducting membrane and into a cathode catalyst layer where you drive the reduction of oxygen. This reaction is typically the harder reaction, or is the harder reaction in a fuel cell. And in this reaction, you have to move both oxygen gas into this porous reaction layer, move protons into the porous reaction layer, and move electrons into the porous reaction. So the transport in this three-phase region of electrons, ions, and reactant is very complex. And so we need to understand how to describe that in terms of a porous electrode theory to understand how these devices really function. So let's start with some definitions. Here is our schematic of a porous electrode, our idealized architecture. We're going to define the front of the electrode as the edge of the electrode that's next to the electrolyte. So we're going to think about the electrolyte over here, okay? And the electrolyte is permeating into the pores. The back of the electrode is the edge of the electrode next to the current collector. We call this the current collector because it is where either the electrons are coming from or the electrons are going into the external circuit. And we're going to assume that this current collector has a constant potential. What that means is that it is a very good electrical conductor, so it can move charges with zero potential drop relative to the potential drop, the size of the potential drops that will develop inside our electrode. So that's an assumption. We're going to define the back surface as x equals 0 and the front surface of x equals L. We're going to be talking largely about one-dimensional models where this is position x going from x equals 0 to L. Inside this electrode, the reaction rates are going to vary with position due to transport and kinetic phenomena. Porosity is defined as the empty or void portion of the electrode. The superficial area is the area of a plane cutting through the electrode normal to the direction of the superficial current. So the superficial area is going to be the area of this cross section here. And we'll define another area, the microscopic. So the specific interfacial area is the actual physical surface area of the electrode in contact with the electrolyte, divided by the volume of the electrode. So if we think about adding up all this area here, all the internal area, if we integrate all that internal area and add it up, and then we divide by the volume of the total electrode, that's going to give us specific interfacial. We'll talk about these more, but you may need to go back to these definitions in order to understand the following equations. So let's think about how current is distributed inside such a porous electrode. Imagine you're doing a reduction reaction on the surface of this electrode. So what do I have to do that? Well, I have O, oxidized species out in the bulk electrolyte. They need to get inside the pores somehow via transport. In this case, we're going to primarily talk about diffusive transport. Then the electrons in the metal electrode are going to have to transfer onto that O and turn it into R. And then the R is going to have to diffuse out. Okay, and those are the processes. Of course, the electrons in the current collector need to transport to the location where they drive the electrochemical reaction. Electrochemical reactions at the outer edge, the electrons are going to have to transfer farther, in contrast to electrochemical reactions at the back, where the O and R are going to have to travel farther. And we'll see how this affects the response of a porous electrode. So we're going to define I1 and Phi1 are the electronic current and electric potential inside the solid phase. This is the solid phase is the electrode material, not the pores, the actual material, the sort of shaded purple gray in this case. So we're going to have some current, I1, flowing in the solid. We're also going to have an electric potential gradient, Phi1, that's driving that current, because this could be a resistive material and it could take some electric driving force, electric potential driving force, an electric field in the solid to drive that current. But there's also a current flowing in the electrolyte called the secondary current. So I2, right, I2 is flowing through the center of the electrolyte out of the cell. It's the ions that are carrying the ionic current. And Phi2 is driving that ionic current due to a gradient in electric potential in the electrolyte phase. So this is where porous electrode theory gets a little bit confusing. You have to keep straight the current and the potential in the solid and the current and the potential in the pores. And both these are happening in the same volume of porous electrode. So let's think about what this means. At x equals 0, we have all solid phase. We have just current collector. Remember, this black piece is the current collector. So the current density, I1, is just the total current divided by the area at x equals 0. So we're going to define big I is the total current. And you'll have to get used to these engineering symbols and units, which are a little bit different than we used in Barton-Faulkner for analytical electrochemistry. But it's good to be able to switch back and forth between the two. So this is going to be current density in solid. Now, at x equals 0, you only have solid, so all the current needs to be in it. Likewise, I2, which is the current in the electrolyte, at x equals L, has to also be equal to I over A, because again, all the current is now flowing in the electrolyte. The solid is gone. And current through this whole device is continuous. So the sum of I1 and I2, no matter where you are in the cell, remember these are each a function of x, no matter where you are in the cell as a function of x, the sum of these currents has to be equal to I over A. Okay, so that's just sort of some definitions of how we think about the current distributions in a porous electrode. Okay, so let's go back. A is this specific interfacial surface area. So it's the surface area per volume. And we'll use that and we'll see how to derive those or estimate those values in a little bit. We're going to call IN. IN is the normal current density to the actual microscopic surface. So if I think of a little surface element anywhere on the inside of this pore, here's the sort of curved inside. If I think about a little surface element, IN is the current that's normal to that element. Okay, so IN is coming off that surface. And IN is going to be a function of x, the position x in the cell. So the amount of current, Faradaic current. So IN is really a Faradaic current that's occurring, in our example, taking O to R, but it could be any type of electrochemical surface interfacial charge transfer. Usually we're going to use units of amps per meter squared. So if I take the product of the surface area per volume with the current density per surface area, I get something called the volumetric charge generation rate. This is how much Faradaic current is getting passed per volume of the porous electrode. So it's similar to current density at a planar electrode, except now we're extending it into 3 dimensions and calculating it per volume. Now, we can learn something about how this electrodes work by writing charge balance. So let's think about what this equations mean. So the first equation says that the change in the current in the solid, so in one dimension, this is just d negative di1 dx, right, in one dimension. So the negative of the change in the current in the solid is equal to the negative of the volumetric charge generation rate. And these are all functions of x. Okay, so this is a little confusing, but what does this really mean? It says that if the current in the solid, moving through the solid, goes down, if it goes down, that current has to go somewhere. So current is continuous, so if the current moving in the solid goes down, that current has to transfer across the interface, going from solid to liquid. So it's saying if the current in the solid, the number of electrons flowing through the solid changes, that change has to be manifest in interfacial current crossing the boundary. Similarly, if the current in the electrolyte changes, it is due to current crossing the boundary because current has to be continuous. We can go back and think about this in our very simple electrochemical example. Imagine I just have 2 electrodes, okay? And I have a voltage source driving those 2 electrodes, and they're just planar electrodes. You all know now that electrons are going to flow through this source, and there's going to have to be some ionic current, some contribution to carry the current of negatives and positives moving in the ionic electrolyte to carry that circular flow of electronic current. And this is essentially saying the same thing, is that in the 2-dimensional electrode case, I have to convert all the electronic current into ionic current. And I have to do that at the 2-dimensional boundary. But in a porous electrode, I can convert part of the electronic current to ionic current at different positions, different x positions in the electrode. And that's exactly what these 2 equations are saying. They're telling me how the change in current in the solid or the change in current in the electrolyte as a function of x or as a function of position depends on the interfacial current, which is communicating between the 2 phases. In is sort of the rate at which electrons are transferring from one phase to the other. Okay. And that can be, again, written. You can combine these 2 equations, and you see that the change in current in one phase is just equal to the change in current in the other phase. They have to sum, equal and opposite, they have to sum to 0. That the sum of the currents is just the total current. So this is just balancing all the charges. So keep that in mind. The challenging part about this porous electrode theory is really keeping all the definitions clean and clear in your head so you can understand what the equations mean. So now that we have our definitions in place, we can use the physics that we learned last quarter to understand how charges move and how reactions occur in porous electrodes. And what we're going to do is we're not going to treat the details of this porous electrode. We're going to treat the porous electrode as a continuum with properties that are representative of the porous electrode, porosities and kinetics that are representative of the porous electrode. We'll see more what that means in a moment. We're going to use the Nernst-Planck equation. The Nernst-Planck equation describes transport due to diffusion, drift, and migration, and often has a convection term. Now, Fuller and Harb defines things just a little different than Bard and Faulkner. Ni is going to be the flux that we're used to versus stationary coordinates. So if you imagine I have a fixed plane with a specific area and I'm looking at the motion of species through that plane, that's going to be flux, Ni. Ji is going to be in the solution frame of reference. So the solution might be moving, and so the window I'm looking at, a flux through, for example, through diffusion or migration, is also moving. We're going to primarily be looking at Ni. And so you can think about big Ni as equivalent to the flux we learned about earlier. Ni has 3 different terms. It has a diffusion term, diffusion coefficient times the concentration gradient. This is Fick's first law. And epsilon here we're going to have to define as the porosity of the sample. And what that's saying is that the sample is not pure electrolyte where diffusion can occur. So if the porosity is 0.5, porosity typically goes from 0 to 1. So if porosity is 0.5, you only have half of the electrode is made of electrolyte, and therefore the flux due to diffusion is going to be half of what it would be if you had pure electrolyte. So that's a very simple modification of our Nernst-Planck equation that we've used before. The same is true for the drift or migration term. Remember, drift or migration, they mean the same thing. It's motion of a charged particle driven by an electric field. An electric field is, of course, a gradient in the electric potential. And it depends on the charge of the ion, its electric mobility, charge carrier mobility, how small it is. So smaller ions have higher charge carrier mobilities, for example. Its viscous drag with the electrolyte. Mobility in solids depends on where the ionic site is and how the energetics of hopping from site to site, these sorts of things. Faraday's constant, and of course the concentration of species. So this all goes into the flux of a given species. And notice we also have this epsilon term here, which again just describes what fraction of the phase are the ions, in this case, able to move through. And then we have our convection term, which also has epsilon, the porosity around it. So we're going to have to use the Nernst-Planck equation. We're going to have to define a few other things, though, because in this porous electrode theory, not only do we have drift and diffusion in our porous electrode, right? We have movement of species transport. We also have chemical reactions taking place. Remember O going to R, for example, where an electron in the metal can transfer and drive a Faradaic reaction, and that can happen really anywhere here, depending on the particular system. So we need to take that into account. So we're going to have to define another parameter, and that's the reaction rate of a given species. And that's going to depend on the A parameter, which is the internal surface area per volume, and the rate of the reaction at the surface in moles per time per unit area. The rate of the chemical reaction is just given by the interfacial current, which we defined earlier, the microscopic current per unit area, times the stoichiometric coefficient of the reaction, and n the number of electrons in the reaction in Faraday's constant. You can work yourself out why this is, but it's simple balancing of an electrochemical reaction. O plus an electron goes to R. The stoichiometric coefficient in this case would be 1, and n would be 1. But you might have, for example, O plus 2 electrons goes to R, and other stoichiometric coefficients here and here. Okay, so for a given species, like for example O or R, you would have a specific stoichiometric coefficient, and n would be for the overall balanced reaction. So this gives you the rate of either generation or depletion of a chemical species within the porous solid. And remember, this all depends on X, where we are within the porous solid. So we have another equation that governs transport in addition to the Nernst-Planck. So that equation is the materials balance equation. For the chemical engineers, you've seen this many times. Essentially, this is related to Fick's second law. It's a continuity equation. It says that if I take some element in my cell and I look at it, okay, my porous electrode, I look at that element, that sort of volume element. So imagine I have some element of that pore that I'm looking at here. And I ask, how does the concentration of some species change with time in that pore? Now, of course, at steady state, right, the time derivatives will go to 0. But if you're not at steady state yet, you need to think about what are all the ways species can move in and out of that volume element, and reactions can consume or generate species in that volume. So this is the gradient of the flux. This is basically saying in one dimension how much stuff is coming in along the x direction and how much stuff is going out. But on top of that, we have to account for the chemical reaction, the electrochemical reaction in this case, which I defined in terms of this Jn term related to the actual current density. So in general, the change in concentration with time is given to by how much the flux is changing in and out of a given element, i.e. is there more stuff coming in than going out, or more stuff going out than coming in, or are they balanced? And then what is the rate of the electrochemical reaction in terms of consuming or making stuff in that volume element? We need to modify this very simply for a porous electrode, and we just have to put this epsilon term in here so we can use the actual concentration of the electrolyte and account for the fact that the electrode is not pure electrolyte. Here's again the rate of the electrochemical reaction written explicitly, and we can convert In into the gradient of I2, which is the current coming through the electrolyte. The change in the current through the electrolyte is, of course, given by the interfacial current, because that's what's driving the ionic current, I2, through the electrolyte. Okay, so these equations look complicated, and you might think about them for a while and make sure you understand precisely what each term means and where it comes from, and also read the chapter in Fuller and Harb as you do that. So we're going to switch gears and talk for a moment about how we characterize porous electrodes before we go on to look at some case studies and some trends for how porous electrodes pass current in electrochemical systems. So we talked about the porosity as varying from 1 to 0, and the porosity is defined as the total volume of the electrode. Consider this is a porous electrode, this is a cube, minus the volume occupied by the solid phase, which is always going to be smaller than the total volume. So this is the fraction of the electrode, which is porous. Another way to define porosity is by the ratio of the mass density. So if you measure the density of an electrode and say you find it's at 1 gram per centimeter squared, but you know that the true mass density of a pure solid, you look it up in the CRC handbook, is say 5 grams per centimeter. You know that the porosity of that electrode is 1 minus 1 over 5 equals 80%, okay, 0.8. So 80% of this electrode would be porous because it weighs 1/5 as what a pure solid would. Very simple definition. We also already defined the specific interfacial area as the interfacial area over the volume of the electrode. And now I want to give you an example of how you might estimate the porosity of a given electrode. So you could imagine an electrode consisting of an idealized packed bed of spheres. And so the total interfacial area would just be the number of spheres times the surface area of each sphere, 4 pi r squared. And you take that total area, right, the total interfacial area, and you divide by the total volume of the solid. So we can define that as V, total volume, and we can calculate the number of spheres by taking that total volume and multiplying it by the fraction that is a solid. Okay, this is the fraction solid. And dividing by the volume of solid per sphere. Okay, so if we divide the total amount of solid, volume of solid, by the amount of volume per sphere, this will give us the number of spheres. This leads to a nice expression where you can estimate the specific interfacial area A from purely the radius of the sphere and the porosities. So if you know the porosity and you know the radius, you can get the specific interfacial area. If you know the porosity, for example, via a mass measurement, and you know the specific interfacial area, for example, via capacitance measurement, you can actually estimate the primary particle size in a porous electrode. So we can approximate a characteristic pore size. And the way to think about that is this characteristic pore size is the ratio of the cross-section available for transport divided by the wetted perimeter of the pore. So this is the cross-sectional area for transport, okay? And this is the perimeter of a given pore. And if you take the ratio of those, you get approximately the average pore size. And for spherical particles, this is simplified by the volume of the voids divided by the bed volume, the overall volume, that's the porosity, divided by the wetted surface over the bed volume, that's simply the superficial area. And that gives us an expression actually for the approximate characteristic pore size in terms of the primary particle size and the porosity. From electrochemistry, but another way to get this data, which is used very often ex situ, it's not an electrochemical method, is a gas absorption measurement. And so what you do is you very carefully evacuate all the gas from a porous solid, and then you carefully dose gas back at very cold temperatures. And imagine I have a porous solid, okay, and here's the solid, and there's the pore wall. And at low temperatures, the gas molecules I add, for example, argon or nitrogen, will absorb on the surface only of the pore before filling the whole pore with gas. And so there's models to handle this and to fit this data. And what you can get is you can get actually a pore size distribution. This is the incremental volume, okay, or the fraction of the volume that's associated with a given pore size. And you can see that in this case, this porous electrode has an average pore size of about 50 nanometers and a pretty broad distribution. There's also some very small pores, some sub 10 nanometer pores, and maybe a few larger pores from agglomerates of particles. We won't talk in much detail or any more detail about these type of measurements. They're often called BET measurements from the theory that's used to analyze the data, but these are more properly gas absorption measurements. So let's think a little bit about the effective parameters that govern how ions and electrons move through a porous material. If you think about a porous material, here's an example from your book. Imagine the pore is the white space, and the dark color here is the solid electrode. If you are an ion and you want to get through this maze, the path you take to get from one side to the other is much longer than the straight shot because you have to go around all these blockages. So we have to take that into account. We define that as the tortuosity. It's the average path length for transport through the electrode divided by the straight line distance. So it affects the conductivity. This is the conductivity of the electrolyte. It also affects the conductivity of the electrons of the solid. Here's the effective conductivity is given by the bulk conductivity of a given electrolyte. So how conductive, for example, a solution of sodium chloride would be if you just had it in a beaker. You have to scale that conductivity by two factors. One is the porosity. This is simple. If I say have half my solid phase, half my porous electrode filled with solid, I only have half as much volume for transport of ions. So the effective conductivity of ions is half of what it would be in the bulk. But I also have to divide by the tortuosity. In this case, the tortuosity is probably 1.5 or something like that. And that's also going to decrease my effective conductivity. So this is how the bulk parameters are related to the microscopic model in terms of porosity and tortuosity to give an effective parameter that we can use to model transport in porous electrodes. So we can write the current in the solution phase, this is I2, the current density as the effective conductivity times the gradient in electric potential in the solution, plus Faraday's constant times the sum of all the diffusion currents from all the solutions, right? Because this is the diffusive flux multiplied by the charge on each species. So this is the total current due to migration and diffusion of species in the solution, defined in terms of these effective parameters. The diffusion coefficient, we also have to define an effective diffusion coefficient based on the tortuosity. Okay, let's consider now how to use these concepts to describe the current distribution, so where the current is passing as a function of distance in the porous electrode. We need two assumptions to make this a simple problem. First, we're going to assume there's no concentration gradient in one dimension moving through the electrode, moving through the porous electrode. So what does this mean in practice? It means we're ignoring the diffusion current, we're ignoring the effect of diffusion, and assuming that all the current is being driven via migration. And this is a valid assumption in many cases. we're also going to assume linear kinetics. What does that mean? That means we're using a linearized form of the Butler-Volmer equation. Remember, the Butler-Volmer equation predicts that the current, I, kinetic current, increases exponentially with overpotential, driving force for the electrochemical reaction. We're going to look near the axis. We're going to assume that our overpotentials are sufficiently small. If I zoom in to a sufficiently small delta in overpotential, the current response can be approximated as a straight line. So we're going to use that approximation. So this is the linearized form of the Butler-Volmer equation. You'll notice the transfer coefficients. You'll notice Faraday's constant, RT, and the exchange current density. This term, phi1 minus phi2, this is the electric potential drop across the solid electrolyte interface. Remember, there's an electric potential in the solid, electric potential in the electrolyte, and this is the difference between the two. This is approximately the overpotential. It requires another assumption, and that is that the equilibrium difference in electric potential is zero. And that's actually not usually true, so you have to be a little bit careful with the application of this, for example, in an electrochemical model. But for now, we can think about this as the driving force for the electrochemical reaction, the difference in the electric potential in the solid versus the electrolyte. So this equation, this Butler-Volmer equation, tells me how the current in the electrolyte, I2, changes with position. Because the current in the electrolyte will go up if there is positive current passing from the electrode to the electrolyte. Because that positive current that passes to the electrolyte must be carried by ions in the electrolyte. So I set the derivative of the electrolyte current equal to the reaction rate, the electrochemical current, Faradaic current at the interface. I can take the second derivative of this equation and I get this. And we're going to do this to develop an analytical solution for the current density in solution. So we're going to try to find what does the current density in solution look like as a function of distance. So how do we do this? Well, we need to think about also the current in the electrode. So again, here's our schematic. We have a porous electrode, has a front of the electrode, a back of the electrode, the current collector. It has some thickness L. X is along this direction. The total current, electron current plus ionic current equals the total current divided by area. These are, current densities. And we're assuming that the currents in the solid and the currents in the electrolyte are purely migration currents. Now in the solid, this is perfectly fine. All the current, for example, carried in a typical metal electrode is due to a voltage, an electric field gradient driving the current, and it's proportional. The current is proportional to the conductivity of the electrode. This is the electronic conductivity. We can write the same equation. This is a form of Ohm's law, which you saw last term, for ions in the electrolyte. This is the ionic conductivity. Again, these are actually effective parameters because this is in the porous solid. The ionic conductivity, and if we assume all the current is due to migration, we're ignoring diffusion, we can write it, the total current in the electrolyte, as the electrolyte conductivity, its effective conductivity, multiplied by the driving force, the gradient in electric potential. So we can now use this relationship to write phi2, d phi2 dx in terms of I2 and the conductivity of the electrolyte. So now we have a differential equation. This is a second order differential equation because I have the second derivative of the current density in the electrolyte, and I have the current density in the electrolyte in the same equation. Okay, I've also now here written the electric potential in the solid, the gradient of the electric potential in the solid, also in terms of current, I2, and the conductivity of the solid. So I2 minus I over A, this term together is just I1. And so I've put in for this d phi dx, d phi1 dx, this expression here, where I've written I1 as I2 and I over A. So now I have a second order differential equation which can be solved. Solving this is not something we'll go through in detail, but in order to solve it, in order to understand the results, it's useful to define what are called dimensionless variables. It's very typical in engineering and physics to define these. So I'm going to define something called I star. And I star is going to be essentially the fraction of the current that's in the electrolyte. And it's dimensionless because this I star term has no units. It's a ratio of two current densities, the total current density and the current density in the electrolyte. I'm also going to define dimensionless length, Z, which is the ratio of where you are X in your cell, remember, going between X equals 0 and X equals L, to the total length of the cell. So this is the fractional length. And then I'm going to define something called nu squared. And this is a ratio of the ohmic resistance to the kinetic resistance is one way to think about this. And so you can look at this equation. It comes from these terms in this equation, and it's a way to simplify it. This is related to the kinetic resistance. It has to do with how fast the electrochemical kinetics are. As I naught increases, right? As I naught increases, the equivalent kinetic resistance, if we think about a series of resistors in series, as I naught increases, the resistance of the kinetics goes down. It's easier to pass current as I naught increases. So this is essentially 1 over the kinetic resistance. This is the ohmic resistance. It's related to the ohmic losses in the solid and the ohmic losses in the electrolyte. Remember, this is electrolyte conductivity, and this is the electrode conductivity. And Kr, we're going to define as the ratio of those two conductivities. So I can rewrite this whole differential equation pretty simply. And so this is actually the differential equation we need to solve. So using our newly defined dimensionless variables, we get a second order ordinary differential equation, which can be solved. So what does the solution look like? Well, to get the solution, we need to define some boundary conditions, right? Whenever we solve any of these equations, it's really important to understand what the boundary conditions are. So 2 are pretty obvious. All the current is in solution at the front edge of the electrode, and all the current is in the solid at the back edge of the electrode. So these are sort of our initial boundary conditions, and they're dimensionless equivalents from our newly defined variables here. So I2 equals the total current at X equals cell, L. Or another way to say that, I star equals 1 at Z equals 1. See how that really simplifies our boundary conditions. I2 equals 0 at X equals 0 at the solid surface. So I star equals 0 and Z equals. We can get an analytical solution. It looks like this. It has these hyperbolic sine terms in it. Cosine H is the average, and sine H is the difference between e to the x and e to the negative x. So these are just functions that come out of solving the differential equation. We won't worry too much about the functional form of this equation. Let's look about what it does as a function of various parameters. One thing we're going to be interested in is the local rate as a function of distance in our electrode. Remember, Z is the distance through our electrode. Z equals 0 is right at the current collector. Z equals 1 is at the front surface. So we can take the derivative of I star. Remember, I star is the current in the electrolyte. And that's going to be related to how much current is passing from the solid to the electrolyte, because that's why I2 is changing. I star is related to I2. I2 is changing because we're doing an electrochemical reaction, driving current from the electrode to the electrolyte. So I can take the derivative, this is the derivative of that function, and I can just rewrite that derivative in terms of In, based on our definition of the dimensionless variables and our definition of I2, the gradient in I2 as the specific interfacial area times the normal current, which is what we actually care about. Okay, so now I have an expression also for the current, the actual current density that's passing from the solid to the solution to the electrolyte as a function, remember, as a function of distance x through our porous electrode. Okay, so here's how we can use this to understand electrode optimization. So these are the terms, right? So these are the parameters that can vary as we change our electrode architecture. So what things matter? Well, we can change the conductivity of either the solid or the electrolyte, right? Their ratio matters, and I naught matters, as well as alpha for both. Okay, so let's think about some examples. Here's the derivative of the current, and here's the dimensionless current. So let's start actually with the dimensionless current, I star. So this is the fraction of the current that's in solution. Okay, notice that you go all the way to x equals L. X equals L, this is Z, right? Dimensionless distance from current collector, or x equals L, then all the currents in the electrolyte. If you go to 0, all the currents in the solid, so there's no current in the electrolyte. Now, if V squared equals 1, meaning that the kinetic resistance and the ohmic resistance are about the same, so how hard it is to push current across the interface relative to how hard it is to transport electrons and ions, about the same, then throughout the electrode, the amount of current transporting through the electrolyte is linearly increasing. If I take the derivative of this, this is telling me actually what is the rate of the interfacial reaction. It's telling me that pretty much everywhere in the electrode, In is constant. So the whole porous electrode is working, is passing current from the electrode to the electrolyte, doing the electrochemical transformation I'm interested in. But let's go to another example where nu squared is 100. So what does that mean? If nu squared is 100, that means that the ohmic resistance is much bigger than the kinetic resistance. Okay, and in this case, this is for a specific ratio, kappa r equals 0.1. These plots would look different if kappa r took different values. But in this case, kappa r equals 0.1, meaning that the ionic conductivity is much smaller than the electronic conductivity. So what does that mean? Well, if I look at the dimensionless current density, what I can see is, again, there's a little bit of current that starts to pass right at the electrode surface. Then basically nothing changes. I'm not really changing much the amount of current passing through the electrolyte until I get nearly the edge of the electrode, near the front surface. And then a ton of current starts to pass, and the current carried in the electrolyte increases dramatically. So why is this? Well, because Kr equals 0.1, and because the transport, nu squared equals 100, the transport resistance, the ohmic resistance, is much larger than the kinetic resistance. The transport is dominating the voltage loss in this electrode. And because the ions are not very good at transporting, most of your current passes close to the electrolyte. Remember, the electrolyte is out here. So the electrons are easier to transfer through the solid than the ions through the pores. So the electrons move out, they do the redox out here at the front surface of the cell, and that's where all your current is. And you can see that here. This is essentially a plot, the derivative of the current density is essentially a plot of In, proportional to In, the interfacial current density, and the interfacial current density is largest out at the front surface, where the ions can access easiest. So in this case, most of your electrode is dead. Okay, so this is not an optimized electrode. It's not doing anything in this region. So if you had an electrode with these characteristics, you'd be much better off changing the electrode thickness, reducing the thickness by a factor of 5, for example, and you'd get a higher performance electrode. You can think about other situations. So if the ratio of kappa to sigma, the electrolyte to electrode solid conductivities is 1, these plots look pretty symmetric. So this is, again, the derivative of I star related to derivative of I2, the current in the electrolyte. And so this is related to In. And you can see if the ohmic and kinetic resistances are very similar, you have In is uniform everywhere, whereas if they're not, and it's dominated by transport, you only get reaction near the surface where electrons can move easily. And if they're different, you only get reaction near the back of the electrode where electrons can move easily, or the surface of the electrode where ions can get access to easily. And in the middle, where one of the two has to travel a long distance, you get no electrochemical reaction rate. There's a way to think about this, and there's more advanced analysis you might be interested in seeing in Newman. This is sort of the classic electrochemical engineering text, extremely good text, a little bit more mathematical. And he has a nice picture as the electrochemical cell is an analog, a porous electrode with ohmic resistances representing matrix and pore solution. So the ohmic resistances, right? The ohmic resistances of the electrode would be along this axis. So this is sort of representing sigma, the conductivity. Each one of these resistances is sort of moving an electron through the electrode. And at any given position, you can pass some IN of X through the electrode-electrolyte interface, and then you have I2 carrying current in the electrolyte. Okay, so this is the primary and secondary current distributions, the current in the electrode and current in the electrolyte in terms of an equivalent circuit model, and the overall potential is dropped across this whole array of resistors and capacitors. Okay, and the final thing I want to talk about is this idea of an internal resistance for the cell or the electrode, which is the change in potential with current density. And so this is something we can define. dV di is an internal resistance. And if you go through the math, you can derive this expression. Okay, and it's related to the length of the electrode and the conductivity of the different phases, as well as the kinetics. And so we can look at this, plot this internal resistance, and what you find is the internal resistance is at a minimum where the current passing through your cell is maximum given for a given driving force. And so these are curves for different ratios of kappa to sigma, and a given exchange current density, given kappa, alpha parameter, and you could do this calculation and estimate the thickness of the electrode you want, right? The thickness of the electrode you want to get the optimal, the lowest internal resistance, therefore the maximum current for the electrochemical process you want to do. And that's all we have for today. I look forward to seeing you in class.